Distinguished guests, ladies and gentlemen, good morning. Welcome to the opening ceremony of the IAS workshop on quantum science, which is the highlight of the IAS Nobel Science Week. My name is Melody Calkins, a student from the Department of Public Policy, your MC today. This workshop is organized by the Institute for Advanced Study, or IAS in short. In the following 2 days, we will have 7 speakers coming from different parts of the world to share with us their insights and discoveries in quantum science. Today, we are very honored to have Professor Jian Liu, Acting President of CityU, Professor Jacob Huang, Acting Director of IAS, and Professor Serge Haroche, initiator of today's workshop, here with us. May we now invite Professor Jian Liu, the Acting President, to deliver a speech for us. Professor Liu, please.
Good morning, Professor Serge Haroche, invited speakers, honorary guests, colleagues, friends, and fellow students. It's my great pleasure and honor to welcome you all to this workshop. This is one of the first IAS workshop on quantum science initiated by our senior fellow, Professor Serge Haroche. Professor Haroche, first of all, I would like to congratulate you to express our deepest gratitude and celebration to your acceptance of honorary doctorate degree at CTU last Friday. So congratulations. Thank you very much. Professor Haroche's affiliation with CTU started in 2015 when he accepted our invitation to be IAS Senior Fellow. He and some other senior fellows witnessed the inauguration of IAS in November 2015. So IAS is one of the few such centers in the region, and it aspires to be an international center of excellence for the advancement of technology and innovation by bringing together an interdisciplinary team of world-renowned scholars and researchers, including Nobel laureate as Professor Haroche, to contribute to the solution of pressing real-world problems. With all the great men and the future leading scholars here, I believe we are on the right track. So this week is a very special and auspicious to City University, since we have 3 Nobel laureates visiting us, namely Professor Serge Haroche, Professor David Winland, and Professor Ramahi Lan. So both Professor Haroche and Professor Lan are our IAS Senior Fellow. So we hope Professor Winland will join us, our CTU family, too, in near future. So there are 2 major events this week involving these 3 distinguished scholars, including Professor Ramahi Lan's lecture yesterday, and also today's workshop, making it Nobel Science Week. So this workshop brings together leaders in the field of quantum science coming from different parts of the world. So they will present the latest results in the research in quantum communication, quantum computation, and the quantum measurement. So I think the quantum physics is a major topic of the future development of the City University of Hong Kong. As you know, we recently established the standalone physics department, because historically we have a physics and material science department, and to expand our research and portfolio in basic science and in material science and engineering. So university decided to expand to a single standalone Department of Physics and create a Department of Material Science and Engineering by injecting around 40 new faculty member land. Okay, so this is a huge expansion for our university. So quantum physics is one of the 4 major topics in the strategic plan, development plan of the physics department. So to me, this workshop just initiate. So we are also actively recruiting scientists in this particular area of quantum physics, quantum communication. So I hope you can also introduce us the young, bright scholar, and also, of course, confirmed scholar if they want to join this region very soon. And Hong Kong, I think, is a very nice city for international exchange because until now, we don't spend many money for R&D, only 0.73% of our GDP is spending for R&D. But 2 weeks ago, our new chief executive announced a new initiative. In 5 years, Hong Kong's R&D spending will be double, okay? So passing from 21 billion Hong Kong dollar to 45 billion Hong Kong dollar. I think quantum communication will be one of the important topics because what Hong Kong want to develop, because as you know, China spend a lot of money in the quantum communication, and also we have some giant company around Hong Kong, Tencent, Huawei are all very close to here. From here to headquarters of Huawei is around 30 miles. Okay, so it's very close. So I do believe Hong Kong and CTU can play a key role in this particular period and in this particular area. So we are negotiating with Shenzhen City to form a so-called Great Bay, so Guangdong, Hong Kong, Macau. So we consider all these like San Francisco Bay. Basically, this region represents around 60 million population. Okay, so it's a huge. And in terms of economic power, today it's roughly number 13. Okay, in 5 years, this region, 60 million people will become number 10 in economy, just very close to California, which is important thing for the high-tech development. So this region will nurture a lot of new high-tech companies. So I hope today's and tomorrow's workshop will help us to define the future direction. And also, very importantly, as Hong Kong is a very nice international city, so also spend some time to enjoy your free time to visit. This is a so-called World City of Asia. So I wish all the best for this important workshop, and thank you very much.
Thank you, Professor Liu. Please take your seat. Now, may we invite Professor Serge Haroche, Senior Fellow of IAS and the initiator of today's workshop, to say a few words. Professor Haroche, please.
Before its computer works, I would like to say a few words. First of all, I'm welcome to this IAS meeting in quantum science. I'm pleased to see a lot of young people who are interested in the development of quantum information and quantum technologies. I would like to thank Professor Lu for his kind welcome and for talking to us about the context of this meeting within CTU and also within the vibrant environment of Hong Kong science, academics, and private sector developments. If it doesn't work, it doesn't matter. I can talk without the slides that I have prepared. What I wanted to say a few words about the context and the way this meeting was organized. As Professor Lu has said, I had been appointed a fellow member of the Institute for Advanced Study 2 years ago, and I found it was a very interesting opportunity for me to interact with scientists here in Hong Kong, to give lectures about my own research, and also to organize events of this kind, allowing people from Hong Kong to interact with scientists coming from all over the world and to learn about new technologies and new ideas. And last year I was asked to organize a meeting, and I was free to choose whichever topic I wanted. And I thought that quantum science and quantum technologies was really something interesting due to the big development of this kind of physics in the world. So it was interesting to talk about basic science and also about the promises of this science for future applications in the domain of communication or computation. So I hope that, and this gave me the opportunity also to invite here many prominent scientists and friends, and I hope that we will have nice discussions, not only during the talks, but also during the round table, which will be organized this afternoon, and during private discussions. I would like to say a few words about the way this field has emerged in the past, and this will provide a kind of introduction to the workshop. We all know that quantum physics has played a very important role to develop the technologies which have changed our lives during the 20th century. Many devices that we are using, like the lasers, the computers, the atomic clocks, came from research in basic knowledge brought about by quantum science. But this science, these quantum advances were using knowledge about the microscopic world, but the quantum properties, like the superposition of states or entanglement, were, so to speak, veiled in these devices. You did not need you needed quantum physics to understand the deep workings of the systems. For example, in lasers, you need quantum physics to understand the way atoms interact with light, but the outcome of a laser, this electromagnetic wave, can be described classically. It has a well-defined amplitude and phase, and it's a classical object. In the same way, in the computers, you need to understand quantum physics to find out how semiconductors operate in the transistors, but the currents which circulate in the computer can be described in a classical way. Now, what we are entering now is in a new era in which we try to exploit directly the quantum logic and the quantum superposition to build devices which you could not describe according to classical physics, and in which the quantum logic will bring about new possibilities which you cannot find with classical computers, for instance. So this has come progressively from different advances in theoretical and experimental physics. I think the first point the first breakthroughs that I should talk about has to do with foundations of quantum physics. Very long ago, discussing about the notion of entanglement, the strange fact that two particles or two systems which have interacted remain linked to each other by a non-local link which is impossible to explain in classical terms, has puzzled Einstein very much. And there has been a very famous paper in the 1930s by Einstein, Podolsky, and Rosen, where Einstein discussed that with his colleagues and tried to find out whether it was possible to explain classically the kind of correlations which quantum physics was predicting. And this remained for a long time a matter of, I would say, rather philosophical discussion until John Bell in the 1960s was able to put it in quantitative terms and to find out that by measurements in a real experiment it was possible to find out whether these correlations could be explained classically or not. And this led to the famous Bell's inequalities in the 60s and 70s and 80s, to beautiful experiments performed by people like Clauser and Anna Aspect, which showed that quantum physics was indeed different, fundamentally different from classical physics, and that this kind of correlation, which we call entanglement or non-locality, couldn't be explained classically. So this was really a theoretical aspect related to the foundation of quantum physics. And very soon, other theoreticians tried to see whether this could be exploited. And protocols were invented to use these quantum properties for communication, to allow people to share secret keys which could not be violated according to the laws of quantum physics, and also developed algorithms which could be used if a computer was able to compute according to several passes at once, exploiting superposition and quantum information, and superposition and entanglement. But this remained theoretical, and it would have remained rather academic if at the same time experimentally methods to manipulate and to control single quantum systems were not being developed. Using lasers in particular, it was able to manipulate single atoms, single molecules, single photons, and later on artificial atoms, and try to make them interact and demonstrate simple steps of quantum logic. So you see here you have three domains which have converged: foundation issues, theoretical quantum, theoretical computational science, experimental atomic and condensed matter physics, and the last leg, the last point I would like to mention is that a big issue which was raised at this point was to be able to scale up all this. If you want to do something more, which is more than a toy, which will operate and be able to do things already useful, you have to scale this up and to have a large number of particles behaving in this way. And then you come with the problem of decoherence, the fact that large systems are coupled to their environment and that they very rapidly lose this quantum character. So the research on decoherence and the way to fight the decoherence, especially by developing what is known as quantum error correction or quantum feedback methods, was also very important. So if you add all this, you come to this very rich domain of physics which involve quantum computation. So the issue of whether or not we will be able to build a quantum computer is certainly the most popular one. Everybody, non-physicists are asking this question all the time, but a little bit less difficult and less ambitious that the quantum computer is called quantum simulation. You need only a few tenths of these particles, for instance, in a lattice, in 1, 2, or 3 dimension device, to be able to emulate what happens in real systems at a quite different scale. And if you can do that, you can maybe find new phases of matter which would be impossible to compute with a classical computer, because as soon as you get more than a few tenths of particles, you can no longer solve Schrödinger's equation exactly. You have also quantum communication that I mentioned, and you have quantum metrology, the fact that you can use the non-classical properties of some systems to perform measurements more precise than what one expected before. And this field of quantum metrology is also very important atomic clocks can benefit from this and become even more precise if you use quantum states of collection of atoms. The last example of this is the detection of gravitational waves. These big antennas use laser light, and if the laser light which circulates in the antenna becomes non-classical, then the sensitivity of these already very fantastic interferometers would be increased. So you see that there are a lot of possibilities, and in this workshop we will discuss all of this. I wanted to add also that this is an interdisciplinary topic. You have scientists working in different areas. You have, of course, computer scientists which are interested in the development of new algorithms which will be useful with this kind of devices. You have, of course, theoretical physicists because it raises the issue of the quantum complexity, of the definition of entanglement and how you can quantitatively define all these concepts. And you have, of course, a lot of atomic physics because most of the devices, most of the systems which have been studied are atoms or ions or photons. You have quantum optics because the lasers are used to manipulate these systems. And you have also condensed matter physics because artificial atoms come from superconducting physics and so on. In this, of course, within 7 days, we cannot cover all these topics. And what we'll be focusing on is mainly the aspect of atomic physics and quantum optics and photonics. And we will not discuss directly, for example, superconducting qubits because we don't have any specialists here to discuss that. I want also to say, to conclude, that it's a field which is developing very fast in the world, in many parts of the world. In the US, you have a lot of academic institutions, universities, which work in this area, and you have also private companies, and you all know that Google, Microsoft, and IBM have jumped into the field and are trying to develop devices, make toy demonstrations. They even have a small set of qubits which are ready for demonstrations that you can work with in the cloud. You have also a lot of efforts being developed in Europe, in UK, in Germany, in Austria, in France, in Switzerland, in Israel, which is connected to Europe through the ERC grants. A lot of labs are working in this field, and also private companies. The French high-power computer company Atos is investing in this field. You have also, of course, in this part of the world, a lot of work being done in China, in particular in quantum communication. I am sorry that Professor Pan, whom I have invited, could not come, but he would have explained to us the effort of China in this field. And you have also big efforts in Singapore, Taiwan, Japan, and as we learned, Hong Kong wants to become a big player in this field. Europe, just to conclude, Europe has launched what they call a flagship in quantum technologies, putting €1 billion over 5 years in order to develop this research in the academic world and in private industries, and trying to simulate the synergies, to accelerate the synergies between private and public research. And the 4 pillars of this flagship in Europe are precisely what I have defined: quantum computing, quantum stimulation, quantum communication, and quantum metrology. And I think Europe has also understood that this is not only technology, that the basic, the ground for all this to develop is basic science, the basic research in all these fields. And the idea is to stimulate research, but also stimulate the teaching of quantum ideas to engineers. And so education is also a big part of this project. So that's what I wanted to say. I hope that our discussions will stimulate a lot of interest in many people here. People who are not directly working in the field, is a scientist in material sciences or physicist. I am very happy that CTU is now developing a specific physics department separated from material sciences. So I think it's very important and shows the interest of CTU for developing this at the basic science level as well as the application level. So I wish every of you a very stimulating and interesting meeting, and I think I will stop here, and I'm sorry. I hope that the technology will work better, because I had tried the computer before it worked, and now I don't know what happened. But I said I had only a few slides which were just illustrating what I just said. Thank you very much.
Thank you, Professor Haroche.